The first thing to note about the final exam is sort of the content on it. The content is everything that was on test 1, 2, 3, and 4, plus the new material. And the new material is really, there's two big ideas that we've learned so far, and those are hypothesis tests and confidence intervals. We learned those in two contexts: one proportion tests and confidence intervals, and two proportion tests and confidence intervals. And so those are the four sort of new ideas that are also on this test. So it's really the entire semester. Now, the format of the test, as I've said before, is it's going to be 20 questions long, approximately. It's very likely going to be exactly 20. That's sort of my goal here. And there's going to be probably somewhere in the realm of like 6 to 8 longer questions. Now, I've said this in an email before, but what are the topics of these longer questions? Students always want to know. I can almost guarantee that, let's think about what we saw in this semester that feels sort of long and substantial. Early on for tests 1 and test 2, it was a lot of descriptive statistics and sort of the normal model. Sort of, we have test 1 that was on categorical data, test 2 that was on quantitative data in the normal model, and test 3, which was correlation, regression, data collection, test 4, which is probability and sampling distributions. The test 1 and test 2 material is now probably going to be peppered in throughout the other questions. We're probably not going to have one question that's like 8 questions about histograms or box plots or something. We're probably going to ask you to interpret a box plot or a histogram in the context of another question, because we have so much more we can ask now. Probability fundamentals is probably the first, I strike that. We'll come back to that. It's not the first though. The first material we encountered in this course that is really sort of gets a long question that makes sense that would happen on the final would be regression and correlation. There is very likely on your test for test 3, there are like 3 different long questions about this. There's probably going to be one long question about regression and correlation on the final. Then there's going to be probably a probability fundamentals question. So that's like the addition rule for disjoint events, the multiplication rule for independent events. So all those smaller rules that we've learned. Then there's probably going to be a random variables and normal model. So that's the sum or difference of 2 random variables. We then have to take, find the mean, find the standard deviation, and take that to the normal table and get a probability at the very end. And so this was test 3, test 4, test 4. Then there's probably going to be a question on 1 proportion confidence intervals, 1 proportion hypothesis tests, and 2 proportion confidence intervals and or hypothesis tests. We're probably not going to have 2 distinct questions on the 2 proportion material. we're probably just going to have one question that focuses on either the confidence intervals or the hypothesis tests or both. But because that was sort of the most recent material and the most sophisticated, we're not going to, make it disproportionately weighed on the exam. There might also be, so that's 6 topics by my count. There might also be a couple of sentence questions where you have to do interpretations in your own words and sentences. This isn't a guarantee or a promise, but these longer questions and the sentence questions tend to be at the very front of the test, so that the back half of the test really is much shorter questions, so that to help you with the time management, as it were. So if you're getting to be about halfway through the test and you feel like you've taken a lot of time on that, that's okay, because the longest questions are the ones that are worth the most, or the ones that you've been working on. Okay, are there any questions about the exam structure or format before we hop into the content? Okay. Okay, so one student asked, I don't want to say that the rest will be multiple choice per se, but they'll be shorter. So another, for example, I guess there's another type of long question that we might have, which was the marginal and conditional distributions from like test 1. In test 1, that got a long question. In the final exam, maybe we'll ask you a couple like short, like what is the proportion for this? What is the proportion for that? Where you have to do a calculation, but instead of having like, 6 to 10 parts to a question, it might be one, 2, or 3 parts to a question, and you sort of just move on with that. But there will be a fair number of multiple choice and like as well. Then another student asked in the chat, is there a minimum mark we must achieve on the exam to pass the class? And that's a great question. No, there is not. In previous semesters prior to the pandemic, there was a policy in place that in order to pass the class, students also had to pass the final and achieve at least a 50% on the final exam. That is a policy that, due to the pandemic and the shift to online sort of testing, we've dropped that requirement to make it sort of a little bit lower stakes in a sense. So no, you could theoretically, if you've done very well the entire semester, you could bomb the final exam and still pass the class. That's entirely possible, though that doesn't tend to happen, really. Any other format questions? Okay. All right. So, a market researcher wants to understand university students' soft drink preferences. In particular, the researcher wants to know if more than half of university students in the town prefer Coke to Pepsi. A random sample of 50 students from the town is given both Coke and Pepsi to drink and asked their preferences. In the sample, 29 participants prefer Coke to Pepsi. The researcher computes the following information. Here's a 95% confidence interval. all the assumptions and conditions are met, and boom, this is the confidence interval. Write a full conclusion in context. Okay, so this is an example of a sentence question that of the type that I just referred to. You're given all of this information, and then you're given the answer, basically. We could have a question that sort of builds you to get to this answer, but we just gave you the answer here. So we want you to write sentences to do this. The first little note that I'm going to make here is this in context. Lots of students will forget the context part and then therefore lose points. Okay, so let's write this out. So let's do a full conclusion. Since the assumptions and conditions are met, we are 95% confident that the parameter, what's our parameter here? We are talking about proportion, so it's the true proportion of what? Of university students in some town, in the town. What's our measure here? Coke to Pepsi. The true proportion of university students in the town that prefer Coke to Pepsi is between 43% and 72%. Now, a few other notes here. I wrote percents because we usually interpret confidence intervals with percents. If you wanted to say 0.43 and 0.72, totally fine, equally correct. Just don't do 0.43% or something like that. Some other notes here. Of university students in the town that prefer Coke to Pepsi, that's a massive amount of context. I probably wouldn't expect you to say all of those words. If you said true proportion of university students who prefer Coke, that's probably enough. The key thing is that there's some sort of students. Here, I'm not even going to say university students. The key thing is, what are we measuring? And who are we measuring it from? Well, students is where we're getting our data. And it's about preferring Coca-Cola. That's really the key thing here. I am also not a massive stickler for the since the assumptions and conditions are met, because we should only be interpreting these things if the assumptions and conditions are met. It's a good practice to start with that, and especially some other instructors might care more about that sort of phraseology, but I'm not a massive stickler for it. So some sort of acknowledgement of that is a good thing. Any questions on this? Okay. It's also worth noting, let me just write something down here to help you keep track of things. This is a one proportion confidence interval question. Very similar setup, except now we've got hypotheses, same basic stem to the question. This is a one proportion hypothesis test question, again with sentences. The researcher conducts a hypothesis test. We've got our hypotheses here. All the assumptions and conditions are met. And we have a p-value of 0.1610. Write a full conclusion in context. Now, what's the first thing that jumps out at you about this? Maybe it doesn't jump out to you, maybe it just jumps out to me. There are two different ways we have of writing conclusions for hypothesis tests with p-values. What are the two different ways we have? Yeah, so we can either fail to reject the null hypothesis or reject the null hypothesis. And we typically do that with an alpha level, or we have some sort of strength of evidence argument. So we've got two different approaches. We have an alpha level comparison or a strength of evidence argument. And there's sort of pros and cons to each one of these. But the strength of evidence approach is becoming more of what's done in the scientific community. We're using alpha levels sort of less and less when we can help it. Now, which approach should we use here to answer this question? I think there's sort of a default answer here because, yeah, we should use the strength approach because there's no alpha level that's given. We're not told using an alpha level of some value. There's no alpha level given, so we should use the strength of evidence approach. If you are given an alpha level, you should use the alpha level approach. Okay, so since the assumptions and conditions are met, because we are told that, and our p-value, which is 0.1610, is this large or small or very large or very small? What 0.1610, what kind of number is that for a p-value? It's large. This is a fairly large p-value. Since our p-value is so large, we have very weak evidence against the null hypothesis. Okay. Is this a complete answer? Why would you say no? I mean, no is a great guess because I stopped and asked this question. Bingo, no context. That's going to get students often. What the heck is our null hypothesis saying? Our null hypothesis is saying that the true proportion of students, university students in the town who prefer Coke to Pepsi is 0.50. Null hypothesis that the true proportion of university students in the town who prefer Coke to Pepsi is 0.50. Yeah. We really want that context because really there's a massive amount of reading that goes into doing statistics, and we want you to actually be able to describe what these results mean. Being able to attach that context to the conclusion is really helps show that you understand what's going on here in this study. Okay, so this would be a full conclusion here. Now let's look at the parts of it. We've got this sort of like assumptions and conditions statement. We have the p-value with the number given. We don't just say because our p-value is so large. Well, what the heck is the number? What's the number you're saying is large? We have some assessment of the size of the value. Is it large, small, sort of middling? A translation of the size of the p-value to the strength of the evidence. A statement that this is against the null hypothesis. That's what we always say for the strength of evidence. Whether it's strong evidence or weak evidence, it's always evidence against the null hypothesis. And then a description telling us what the null hypothesis is in context. That's really what we're doing here. So those are the parts of this. Now the key thing, some other so this is sort of the end of this question, some basic facts to remember. Bigger p-values are what kind of evidence against the null hypothesis? Yeah, they're weak. The bigger the p-value, the weaker the evidence. Smaller p-values are stronger evidence against the null hypothesis. And when we were really looking for strong evidence is a p-value less than 0.01. That's a rough cutoff. Yeah. So this idea that bigger is weaker and smaller is stronger, a lot of students get tripped up with that. So if you know you're the type of student who does get tripped up with that, write that down somewhere. I mean, this is an open book test, and so you don't explicitly have to make a note sheet like you might if this was an in-person test. But making a note sheet is a great way to study. If I were taking an open book test, I would still create a one-page note sheet with all of the key things that I think I need, and this would be something that I put on it, I think, if I were the type of student who struggled with that and I was taking an introductory statistics course for the first time. In fact, I think when I did take an intro stats course for the first time many years ago, I think I put this sort of thing on my note sheet. Okay, any other questions? Okay. So researchers wanted to study the relationship between venous thrombosis and the presence of a certain cytokine in patients, and that just means do we detect it or not detect it? They collected samples from one group of 506 patients with venous thrombosis and one group of 1,464 patients without. Not sure what that in the one. I'm not sure what that is in the chat. So if you can explain if that's something for me, we'd love that. These groups are representative. We can treat them as random samples. The summarized data are shown in the table below. Okay, so we've got the summarized data here, and what we're going to do is we're going to do a 2-proportion test to compare the cases and controls. Rather than having you do the calculations by yourself, we're giving you Minitab output for you to interpret, really. Okay, so the first thing to note is, what hypotheses are the researchers using? Now, there's only going to be one valid set of hypotheses here. Let's look right away here. Our null hypothesis has to have what sign? Yeah, the null hypothesis has that equal sign in it. And the only one that does is C. It's the only one that has the equal sign. The not equals got us, not equals greater than. Those are all incorrect. The equals is always with the null hypothesis. Which of the following is an approximate expression of the pooled sample proportion used when conducting the two-proportion hypothesis test? Remember, our null hypothesis is that the cases and controls have the same proportion. They're basically the same group. There's no difference between them on the thing we care about. So in order to estimate the true proportion of people who have the certain cytokine, we just lump everybody together. We have this should be the total number with the detected cytokine out of the total number of patients. And so the total number of people who have the cytokine is this, 289 plus 850. The total number of patients would be that. And so that would be it. Okay. Now, as a little note, if you really wanted to, I believe you could check your work here. 289 plus 850. This is 1139. 1139 divided by 506 plus 1506 plus 1464. This is 1970. 1139 divided by 1970 is, hey, look at this, 0.578172589, which rounds to that. In the Minitab output, it tells us the pooled estimate of the proportions. If you weren't sure about it, whatever your answer is to here should give you this number, if you're given this exact type of output. All right. The next question says, well, okay, why is the pooled sample proportion used? And the answer is, so A says the formula for the standard error is this. And this is not true. This is the SE for a one proportion confidence interval. So it's not just, I mean, A, why do we use it? The answer is probably not because the formula says so. There's a more nuanced reason for that. But this isn't even the right formula. So A is not it. When constructing a confidence interval, we do not use the pooled sample proportion. Mathematically, confidence intervals and hypothesis tests cannot use the same standard error. This is not true. We just don't, this is not a factual statement here. The first one is, when constructing a confidence interval, we do not use the pooled sample proportion. Sure, that's a true fact. but there's no reason why we have to use different standard errors, and that doesn't even explain why, if that were true, why we do use the p-hat that we do. C says we assume the null hypothesis is true. That's correct. Pooling all of the successes together reflects the null hypothesis. Yeah, that's exactly what we did here. We added 289 and 850 because the two groups we treat them as the same under the null hypothesis. And D says we don't even use the value, we use p null, which is 0. And that's not true in this case because we don't have a single p null value, we have a null for the difference. Okay. All right. The next thing we need to do is identify the test statistic. What is a test statistic that we're looking for here? What sort of thing are we trying to find? Yeah, it's a Z value. And so we're just going to go ahead and take this Z value right here, negative 0.37. And the p-value for it is 0.710, which is here. We use the normal approximation approach. We do not use Fisher's exact approach. You'll learn Fisher's exact test if you take Math 283. You'll learn that approach there. You might also learn it in some other classes. There's some advantages to Fisher's exact approach, but that approach is generally used when we have small sample sizes. And we didn't learn about it in this class. So the p-value that we use that goes with the test statistic is 0.710. So what conclusion should the researchers reach? Well, this is a very large p-value. Because the p-value is so large, we have very strong evidence against the null hypothesis. No, we don't have very strong evidence. Because the p-value is so large, there is essentially no evidence that the two groups have different population proportions. That's true. This is it. This is the answer. The next one is wrong because it says there's no evidence that the two groups have different sample proportions. The statistical inference we do is about the population proportions, not the sample proportions. Because the p-value is so large, we have proved that the two groups have the same population proportions. We don't prove things in statistics. We document evidence about them. We don't make a definitive yes or no statement. Okay, and then we have this confidence interval part. Complete the interpretation of the confidence interval. We are 95% confident that the true population proportion of people with VT in whom the cytokine is detectable is between, we're talking about proportion, so we're just going to use these values here and round them to 3 decimal places, negative 0.059 and 0.041, larger than the population. Do we reach the same conclusion using the hypothesis test and confidence interval? Well, we just said that there's no difference. What we're really asking for is 0 in here? And sure enough, this is negative, this is positive. Between a negative and a positive, you have 0. Yes, we do, because 0 is in the confidence interval. If 0 is in the confidence interval, we think no difference is plausible. And no difference being plausible is what we just said here for the conclusion in 6. Okay. Any questions before we mosey on to the next one? All right. So we have a table with some probabilities and a missing value here. This is a probability fundamentals question. What is the probability that a randomly selected adult's highest level of education did not complete high school? Well, these account for all of the education levels that we have. And so we're going to do 1 minus 0.24 plus 0.34 plus 0.28 using the complement rule to get 1 minus 0.86, which is 0.14, 0.14, 0.14. What is the probability that a randomly selected adult's highest level of education is bachelor's degree or graduate degree? Or means we should be thinking addition rule. Now, why can we add these two together? Why can we do 0.34 plus 0.28? Well, somebody's highest degree cannot be a bachelor's degree at the same time that their highest degree is a graduate degree. You can't have both as your highest. One of them is your highest degree. So these are disjoint events, and so we can add these together to get 0.62 for disjoint events. Which probably, oh, that's Doug, read your questions. Which probably rule do we use? Addition rule for disjoint events. It's important to note that only two of these rules are real. This is a real rule, and this is a real rule. The other two rules here, there is no such thing as the addition rule for independent events, and there is no such thing as the multiplication rule for disjoint events. Those rules don't exist. There is a general addition rule that we didn't talk about, and a general multiplication rule that we didn't talk about. But our special rules that we have are addition for disjoint, multiplication for independent. What is the probability that 3 randomly selected adults all have high school diploma as their highest level of education? So we're going to sample the first, sample the second, sample the third. High school diploma, 0.24, 0.24, 0.24. We're going to multiply these together because 3 randomly selected, those are going to be independent draws. This is 0.24 cubed. This is going to be about 0.0138. 0.0138. And we just use the multiplication rule for independent events. And that's that. It is worth noting, I would review, if you strongly encourage you to review test 4 for this question. You access your, if you've forgotten, you can access your old assignments through the review link on the left side of the MyLab. I can't show you that because I don't have any assignments because I have the instructor account, so I can't show you how to review your assignments. But the review button is where you can review your test. There's a probability question on that test that is a bit more complicated than this one. Make sure you know how to do that one. That's a very classic kind of probability problem. The manager of a local fast food restaurant is concerned about customers who ask for a water cup when placing an order, but fill the cup with a soft drink from the beverage fountain instead of filling the cup with water. Stealing soda, or pop, or whatever we call it up here. The manager selected a random sample of 60 customers who asked for a water cup when placing an order and found that 18 of them filled the cup with a soft drink from the beverage fountain. Construct and interpret a 90% confidence interval for the proportion of all customers who, having asked for a water cup when placing an order, will fill the cup with a soft drink from the beverage fountain. Ugh. And we're going to sort of walk you through this here. I will say that this sort of question is a sort of a nice thing from online tests. We might have in a paper test, sort of in the pandemic days, we might have this question just without the steps you through it, like do the whole thing, go. So I like that. I like sort of the structure of helping you walk through this. So first off, is the independence assumption met? What is the independence assumption here? The independence assumption is that whether one customer fills their cup with pop instead of water, that shouldn't affect whether another customer fills their cup with water instead of pop. Because we take a random sample of customers, we think that that should be true. Because we have a random sample of customers, we should have this independence assumption met. If the manager just selected willy-nilly people who came in, maybe they would say, oh, I'm going to watch these like 5 obvious, friends who come in, and maybe peer pressure might call, if one of them wants to fill their cup with pop, maybe they'll all fill their cup with pop or something. Or maybe peer pressure will help them be good, and if one wanted to steal pop, their friends not doing it will convince them to not do it. That would very clearly violate independence. And so that's why we take the random samples. We don't have that occur. So how many customers in the sample did not fill the cup with pop? Well, 62 customers were in the study. 18 filled it with pop. 44 did not. All right. Is the sample size assumption met? We're doing a confidence interval here. So our sample size assumption is at least 10 successes and at least 10 failures. And so, yeah, it's met. We have 44 failures, as it were, and 18 successes. And so we're good. Yep, our sample size condition is met. It is important to note that in this class, we typically do not check this 10% of the population condition. We don't typically do that, even though your textbook talks about it. The reason why we don't check the 10% of the population condition is because if you happen to sample more than 10% of the population, it actually doesn't hurt your results much. It's just that you can and should do some other steps to make adjustments for that, but they're making your confidence intervals more narrow, which is a nice thing. And so it's ignoring that condition doesn't really get us into trouble, as it were. Our results are more conservative than they otherwise were. Okay. And there's only so much we can talk about in this class, so we pick something that's one thing we choose to not focus on as much. Math 2284 is where you would talk about the adjustments that you would do in exactly those situations. So what is the sample proportion P hat if customers filled the cup with a soft drink? 18 of the 62 did, which is about 0.2903. Okay. What is the standard error of the sample proportion P hat? Well, our standard error is the square root of P hat times 1 minus P hat over N. 0.2903 is 1 minus 0.2903 divided by 62. That is about 0.0576. What is the margin of error for a 90% confidence level? The margin of error is our Z star multiplied by the standard error. Z star for a 90% confidence interval is 1.645. And that's basically, you just should know that or have that written down somewhere. You could get that from the normal table, sort of working backwards, but you don't need to. That's sort of a standard value to just know. 1.645 multiplied by 0.0576. That is about 0.095, which is following is the best interpretation of the 90% confidence interval. There is a 90% probability that the true proportion lies between 19.6 and 38.57 or 38.5%. This is not true. There's not a 90% probability. Either the true, in the statistical approach that we use, we believe that there's a true fixed number out there. Either it is between those two numbers or it's not. There's a 100% chance or a 0% chance. There's not a 90% probability. So talking about the probability for confidence interval interpretation is not appropriate. We are 90% confident that the true proportion of customers who request a water cup and fill it with soft drink is between 19.6% and 38.5%. Yep, this is a good one. 90% of the data in the population falls between 19.6 and 38.5%. This is a nonsense statement. It might be harder to see next semester when we get into a different type of data and we're doing these for means. But right now, the data we collect from these customers is a yes or a no. Did they steal pop from us or not? Yes or no. What does it mean for 90% of the data, 90% of the yeses and nos to be between 19.6 and 38.5%? That is gibberish. And then we are 90% confident that the sample portion of customers who requested water cup and fill it with soft drink is between 19.6% and 38.5%. It's not the sample portion. We don't need to make inference for the sample portion. We know the sample portion. It's 0.2903. That's it. There's no confidence necessary. Z star for 95% is 1.96. I'll just type that in the chat there. And if you want 99%, it is if the manager had chosen to construct an 80% confidence interval instead of a 90% confidence interval, so they are less confident, what would be true? Well, the less confident you are, the narrower your predictions can be. Inversely, the more confident you want to be, the more wiggle room you've got to give yourself. So that if they wanted to be 99% confident, you'd have to have a much wider confidence interval. If they're okay with being less confident, they could have a narrower interval. So 80%, and what's going to happen there is that this number, Z star, is going to shrink. 99% is 2.576. 95% is 1.96. 90% is 1.645. 80% is a smaller number still. So the interval would be more narrow because the margin of error would be smaller. The only place in our calculations where the confidence level pops up is this Z star. That is it. It doesn't actually affect the sample proportion at all. A professor wants to know if more than 10% of students at a university enjoy watching baking competition shows. To do this, he takes a random sample of 151 students, of which 25 say that they do enjoy watching these shows. Is there convincing evidence that more than 10% of students at the university enjoy watching these shows? Okay. What is the parameter of interest in the study and its value? The parameter is the value from the population. I'm not a big believer in mnemonic devices, but P parameter population, S sample statistic. Those are sort of the ways to remember. The parameter is the population value, and we generally don't know it. We do not know the true proportion of students at the university who enjoy watching baking competition shows. So it is this. What is the null hypothesis for this study? Well, our null hypothesis is the parameter, the symbol for the parameter, generally. In this case, P for the true proportion, an equal sign, and our null value. We want to know if more than 10%, so our null value is 10%. We do not use the p hat, so do not use p hat symbol or p hat value in your hypotheses. We do not use them. So the alternative hypothesis is going to be p greater than 0.10. We do not use the p hat symbol or value in the hypotheses. So anywhere you see p hat or 0.17 would be incorrect for 2 and 3. What is the standard error of the sample proportion, p hat, in this study? In this study, because this is a hypothesis test for one proportion, our standard error is p null times 1 minus p null over n, which is 0.10 times 1 minus 0.10 over 151, which is about the square root of 0.00596026, which is about 0.024413654, which is about 0.024. What is the value of the test statistic Z in this study? Well, Z is going to be p hat minus p null over the standard error. This is 0.17. This was rounded. This is an example. I think I warned y'all in an email that there's some quirky values to this practice test. This is an example of one of those quirky questions that was sort of a product of me not being super familiar with the MyLab system back in end of November 2020. This is like 2.87. I believe anywhere from like 2.87 to 2.92 was accepted here. Let me just see what the actual 2.92, or what am I doing? 0.17 minus 0.10, 0.024. So I get like 2.92. It's sort of awkward. You might see on MyLab sometimes the answer doesn't quite make sense that it shows you as the correct answer. The reason for this is if there's multiple answers that are marked as correct, it kind of just picks one to show as the correct answer. I can't control which one it picks. So even though I calculate 2.92, it might display like 2.87 to you as a correct answer because that might be marked as a correct answer for this. Then the p-value for the study, we go to table Z. I don't have a table Z handy, but we would look up this, and table Z is going to tell us an area to the left of, say, 2.92. And it tells us 0.9982. So do 1 minus 0.9982 to get 0.0018. And then, which of the following is the best interpretation of the p-value for the study? Because it's so small, we have very strong evidence against the null hypothesis. It's worth noting, again, I am very aware when making the tests now that there is a spot that rounding occurs here, rounding occurs here, rounding occurs here, and then that can affect the value that you look up on the table. I try to have various ways of accounting for that now when I write the questions. So this question in particular is quite awkward on the practice test for that reason. I'm hoping that the next time we have in sort of the next semester, we might be able to use a more recent final exam as the practice test. That's my hope. Okay. Any questions on this? Oh, I guess there's another part here. All right, what's the summary of this of the results? I proved the 10%. Nope, did not. You never prove anything in statistics like this. I found very weak evidence that the true proportion. No, not very weak. We just said it's quite strong evidence. I proved that 17. Nope. Proving. Nope. No. I found that very strong evidence that the true proportion of students who enjoy watching baking shows is exactly 10%. Nope. We found very strong evidence against that. I found very strong evidence that the true proportion of students at the university who enjoy watching baking shows is more than 10%. Yes, this is our winner. I found very weak evidence. Very weak? No. Okay. Looking at the test now, it looks like we'll probably have time for one more question this review session, and we'll do the remainder of them in the next one. And if we need more, we'll do a third one. Okay. In 2020, the percentage of Canadians who live in the Atlantic provinces is 6.4%. A group of researchers randomly samples 400 Canadians and wants to determine what proportion live in the Atlantic provinces. For random samples of size 400, what are the mean and standard deviation of the sample proportion? Well, the mean, the center of the distribution, is the true value. We know the true value is 0.064, 6.4% as a proportion. The standard deviation is going to be the square root of p times 1 minus p over n. This is the square root of 0.64, 0.0. Now, Doug, use the eraser tool. 0.064 times 1 minus 0.064 divided by 400. This is about 0.012. Note something really important here. While this formula looks familiar, we use the true value. In this case, we know the true value. And so this is really a sampling distribution question. So we only use p hat or p null when we don't know the true value. Okay? Using the 68, 95, 99.7 rule, approximately 99.7% of random samples of size 400 will have a sample proportion between blah and blah, centered at 0.064. 99.7%, that is 3 standard deviations plus 3 standard deviations minus 3 standard deviations. So what we're going to do is we're going to do 0.064 minus 3 times 0.012 and 0.064 plus 3 times 0.012. And we get 0.027 and 0.101. Now we're going to find the probability that more than 8% of Canadians in the researcher sample live in the Atlantic provinces. What would the Z value for this be? Our Z value here would be p hat minus p over the standard deviation, which is 0.08 minus 0.064 divided by 0.012. And this is going to be equal to about 1.31. Which part of the normal curve do we want to look at here? We want to know the probability 0.64, 0.08, more than 8%. So we're looking at the right upper tail area. Then what is this probability? Well, we're going to look up on the table, on table Z, 1 minus 0.0951. We will find 0. The table will say this, and we will do 1 minus 0.9049 to get 0.0951. And then if researchers were to take another random sample size 800, how would the probability of more than 8% of Canadians sample change here? Okay. What's going to happen? Let's take a look at this. What happens to the probability if we use 800 here instead of 400? Well, this is going to get smaller because we're dividing by a larger number. If this is smaller, then this whole thing gets larger because we're dividing by a smaller number. So the Z value gets larger. If the Z value is larger, then this will get larger, and so this will get smaller. A lot of little steps there. The sample is less likely to occur because the standard deviation of the statistic is smaller. That is it for this question, and basically all we have time for in today's review session. We will continue with the next question, this regression one, in tomorrow's review session. Are there any other questions?